This isn't going to be a particularly technical talk. I'm mainly going to give you a sort of use case and a view from the trenches. Okay, so the project is the European Holocaust Research Infrastructure Project. And mainly what we're dealing with is electronic descriptions of what material exists in archives around the world. And we're specifically focusing on Holocaust-related material. We're also creating new electronic descriptions of things where they don't already exist. The other goal is to sort of virtually link things together which are related. For various historical reasons, a lot of Holocaust-related material is quite fragmented. So material that should exist from one particular source will be spread around many different archives. And so the goal is to put that into one place where people can find sort of what exists where, and to sort of assemble it into virtual collections. So the data we get from all these different archives, if it exists at all, is quite varied. But one particular characteristic it always has is it's arranged hierarchically, much like the files on your computer or the physical material in the archive within a shelf, within a box, and so on. Now, we worked a lot with some various other tools that did this, which were mostly based on a MySQL database or something. And one of the pain points was always dealing with this hierarchical structure. I mean, obviously it's very doable in a standard relational database to do this, but there's usually some trade-offs. And the biggest trade-off in our mind wasn't so much the performance, it was really the complexity that it added in, sort of adding and moving stuff and just maintaining sort of an easy-to-use. So we went for a graph database mainly because we've got quite an evolving data set. Every time we get new data, we sort of have to change something. There's lots of generic functionality, so we're not just dealing with just these archival descriptions. There are many different entity types that are related, such as descriptions of people, places, and so on. And we want to treat them in a very generic manner. And we also have, which I'll get to in a minute, the sort of social relation aspect, which is related to how the people are going to use this data. Now, it's not just a case of putting it all together and sort of exposing it to the world. Unfortunately, we had to deal with a lot of sort of boilerplate plumbing. As I said, we have people creating new data, and historians tend to want to sort of see something and then immediately change it, and then other historians will disagree with that. So we have things sort of divided into, say, a person will be able to edit things just related to the country that they're sort of responsible for, or just a particular archive they're responsible for, or just the collection. So again, it follows this structure. We also have a sort of legal requirement to restrict access to certain data, which is, in my mind, a bit silly, but it was written into the project plan years ago, so that's that. As I said, we really don't want to end up making a social network, a really tiny, rubbish version of Facebook, but we do have certain functionalities that have this sort of social aspect. So people can mark up data, they can share data with each other, and they can collaborate in sort of assembling these sort of virtual representations of archival material. So it's basically the stack we're using. We're using Neo4j, and then on top of that we've got the Blueprint API. For those who aren't familiar, Blueprints is a sort of abstraction layer which theoretically enables you to plug in another graph underneath, like sparsity's graph or Titan or something like that. And then that's exposed via a web service. It does all the sort of boring heavy lifting of making sure with permissions and CRUD and what have you. So, just a tiny bit about sort of the nature of the traversals we do. I mean, a lot of them are very simple, obviously, but a lot of them are following these hierarchies up and down. So, for example, there's hierarchies in the material itself, or what users belong to particular groups, which can have multiple sort of layers. And so we do a lot of sort of traversing when we don't know how long the path is going to be. And this is something that is sort of very easy in the way we're doing it with mostly coding in Java. It's also quite easy with Cypher. It was something that was quite difficult with sort of the early versions of Sparkle, but I think it might be a lot easier now. And another thing we're doing is to wrap the low-level representation of the graph in such a way that we can simplify everything else by creating a view of the graph for a given person. So, for example, if an item is restricted in access, most items aren't restricted, but if an item is restricted to a particular person or a particular group, then we can create a virtual representation of the graph that only sort of other users are allowed to see. And essentially this simplifies everything else, so you don't have to sort of put your access control in half a dozen other places. You can just do it once. And I think that's quite nice, and it's made popular by the sort of lazy traversal manner that blueprints and Neo4j work. And this is something I'll come back to. I thought this would have quite a performance overhead, but it turns out I know nothing, and there's almost no performance overhead whatsoever in practice. We want to be able to expose our data as a sort of in RDF and allow people to query it with Sparkle. We're using some of the tools in the Blueprint suite, Tinkerbox suite, to convert from the Neo4j data, just sort of nodes and vertices, into RDF. The issue we then want to address on that is to actually map it from this sort of, this is a node, this is the properties and edge, to something more, a higher level sort of domain representation. We're looking at in ways to sort of infer this, but I am far from an expert in this thing, so if anyone has any sort of good ideas for ways to do this, then please let me know. Performance. Now I've put this picture because I often feel that whenever I'm sort of looking at performance issues, that they tend to be quite sort of phantoms, and they'll appear one day and disappear the next. Now we're not dealing with big data by any means. I mean, the 1 million nodes was something I pulled out of the air, but for example, if we have 100,000 sort of actual sort of just archival descriptions, this would translate to sort of maybe 1 million nodes. Then it'll probably be some top of that. So it's in that order of magnitude. The number of users we get will depend on how sort of interested people are in the project, and in particular if we get sort of genealogists interested, then we could get quite a fair bit of users. We've basically seen with Neo4j almost sort of no performance problems, as you might expect from this relatively small amount of data. But still, performance is important, and performance in terms of getting the data in and also sort of reading the whole thing to re-index the whole data set. Performance problems tend to be difficult to track down, mainly because the servers we're using are sort of managed by someone else, and I think a lot of them seem to be sort of cold caches in Neo4j, and just the servers lying to us about how much memory they have. But unfortunately, we can't just sort of order up another 8 gigabytes of RAM and throw that in and fix everything. So it's, we do have some sort of genuine concerns there about sort of trying to get the best performance out of the graph. The challenges. Clearly, the flip side to sort of having a schemaless model that allows you to evolve the data set very easy is that it's not so easy to keep it sort of all working in production. Neo4j have started sort of adding some more sort of integrity checking features in their latest 2. We're still on 1.9. We've had to sort of do a few things I don't particularly like in order to ensure that we can sort of maintain the integrity of the data. What we really like is a nice sort of declarative way of specifying the schema that we could then sort of validate our graph with. So it wouldn't happen sort of at insertion time, but we could check it every now and then fix problems as they come up. At the moment, this sort of basically involves writing a whole bunch of Java code, which is far from perfect. So again, we're looking at solutions like exporting it as RDF and then trying to sort of write rules using the various tools within the linked data ecosystem to do that. But again, this is sort of early days. challenge is in sort of versioning the data. We version things as changes are made, but it's far from perfect. Basically, it's quite trivial to version just a node and its properties, even a well-defined subgraph. It's quite difficult to validate all the changing nature of the relationships between those things. We're very interested in Datomic, which I'm sure many of you are familiar with. It's a sort of triple store with the added time component, and that allows you to sort of roll back and do queries from any point in the past. I think Davey Subi is here. He wrote an implementation, a blueprint implementation for Datomic called FluxGraph. So in theory, if we can get all this to work, we could just plug that in instead of Neo4j and then experiment with a sort of time-centric view of our data. But this is, again, early days and quite experimental. So I think that using the graph database with the blueprint stack has reduced a lot of friction because it makes the sort of structure of our data much more obvious, much less complex for the sake of having to do the modelling itself. The people who have to maintain the project after us may disagree, whether it's because we've had to sort of, it's a fairly new thing, isn't it? It's not quite so mature as the standard RDBMS. I think that the work that the LDBC and other groups are doing with this benchmarking is really important, mainly because I'm quite bad at sort of making assumptions which turn out to be accurate in terms of what's going to be fast and what's going to be slow and why. So this is very relevant to us, I think, and I think it will help developers like me make better decisions in the future. So I'm not sure how I'm doing with time. Maybe,
You're great. I mean, I was about to give you your Easter egg.
Okay, well that's good, because I've just finished. Super.
Okay, thanks. Have a specific question, right?
I guess you use EAD to represent the model.
We do, yes. It's sort of the nearest thing to a sort of standardized format, but of course EAD is, there are lots of different types of EAD. And the EAD from two different archives will tend to look radically different in the way that they represent the hierarchies in their data.
Well,
so,
do you liaise with the Apex project? They have Apex. It's a related.
Yes, we have some overlap with them, like some of the archives work with Apex and they can just give their Apex EAD to us, and that's very handy. Once we've narrowed it down to a subset of the material that's most relevant. We're also working with Archives Hub. They're another sort of aggregator that deals largely in EAD. But for most of the institutions we're working with, I mean, the typical situation would be them to give us a spreadsheet or something. I mean, there just isn't enough penetration of standardized representations of these descriptions to make a the platonic ideal of just getting lots of XML and shoving it in an XML database and then indexing it. As I said, the data we get, it's mostly metadata, so it does have to go into, for us to work with effectively and for us to link things together, we have to take that raw data and put it into the graph to allow for more dynamic handling of that material.
And I don't know what are your RDF requirements, but there is quite a lot of organized effort to convert the XML to RDF in the CDOC tool.
Yeah.
In fact, there was a work group just 2 days ago we had try and standardize on this. And maybe I can talk to you in the break, but finally kind of like a vocative question. have you considered idea stores seriously for these tasks?
Yes, we have. I must admit, one of the reasons we went with Neo4j was, or rather the blueprint stack, was because it was a more familiar environment to the developers who were doing most of the data integration. And then there were also, as I say, some possibly unfounded concerns about the performance characteristics, mainly based on not very well informed experiences of querying triple stores and finding out that things were quite slow. As I say, this is entirely uninformed speculation, which is one why the benchmarking work is very important. And it may have turned out that had more data existed on the relative performance of these things, we may have taken a different approach.
Hi, and I have Jeff on my heritage and location. I'd really like to join you for the discussion at lunch. I was wondering if you deal with data coming from different archives and different formats. How do you deal with not being able to fully map to, say, an EHRI model, or
So how do we?
does it result in a different format for each data set you receive, or do you enrichment by?
Essentially, we map it to a subset of EAD,
Right. Yeah.
basically. I mean, or generic in-graph representation. But we do have to throw some data away. Some things that are just, being an integration thing we can't take. We try and put stuff in that we're not necessarily able to make best use of later. And that's why we had to, be quite dynamic in the way that we handle it. We try not to throw too much data away. We don't want to, for example, force everyone to give us, Dublin core and reduce everything down to that very basic representation. But invariably, stuff does get lost in translation. But essentially, we try and use EAD as the base, or rather, as I said, a subset of EAD as the basic. I'm losing the word now, but the main representation that we write the importers around EAD. So stuff gets transformed or converted into EAD before going into our system.